In this video, we're going to take data for the T1 measurement of mineral oil. So as we left in the last video, we have an application of two pulses, the A pulse right here and the B pulse right here, at some time delay. In this case, it's 10 milliseconds between the two. You hardly see any response on the yellow trace here because of the A pulse. That's because the A pulse is tuned to 180 degrees. But then when the B pulse is applied right in here, you see a very large return from the system because the B pulse is set to 90 degrees, and so off we go. So what we'd like to do then is we'd like to track the amplitude of this signal, the amplitude of this return, as a function of delay time between the two pulses. And I'll do a couple things here. First thing I'll do is I will synchronize the oscilloscope on channel B like this. So this is the B pulse right here. The oscilloscope is forced to trigger now on the B pulse. And that's kind of convenient for us because what I can do now is just zoom in like this and see the full return in a very nice way. And there's the B pulse right there. So there's the B pulse, here's the return signal. So we're going to track the amplitude of this as a function of delay time. So I'm doing the same things with the cursor again. I have one cursor buried down here in the yellow baseline. Another cursor is this dotted line up here at the very top of this peak. And so the oscilloscope will tell me delta Y, in this case about 3.875 volts. So at 10 milliseconds, I'm getting a return signal of about 3.875 volts. So what I'm going to do now is, as we did before, we're going to increase the delay time and monitor the amplitude of this signal as a function of time. It's going to feel very much like the T2 measurement, but it's not. So let me go up to 15 milliseconds. So at 15 milliseconds, you can see the amplitude is dropping to about 2.1 volts. Let me go up to 20 milliseconds. And it's getting kind of small. Let me maybe go a little finer than that. So that was 15. Here's 16 milliseconds. 16 milliseconds gives 1.76 volts. 17 milliseconds is giving 1.38 volts. 18 milliseconds is giving 1.05 volts. 19 milliseconds is giving 0.537 volts. And when I finally get to 20, bear with me just a minute here, there's 20. Signal's getting very small. 0.375 volts. 21 milliseconds, about 0.25 volts. Now as I go to 22 milliseconds, surprise, surprise, the signal's starting to get larger again. This is indicative of T1. So 22 milliseconds, 0.637 volts. 24 milliseconds, 1.32 volts. 27 milliseconds, 0.206 volts. Go up to 30 now. 30 milliseconds. 2.65 volts. 2.65. 35 milliseconds. 3.5. 40 milliseconds. 4.25. 4.22. 45 milliseconds, 4.78. 50 milliseconds, 5.38. 55 milliseconds, 5.81. 60 milliseconds, 6.26. 65 milliseconds, 6.61. 70 milliseconds, I'm going off the screen just a bit, so let me adjust the oscilloscope here. Let me move this down. The cursors are following okay. Go up. So 70 milliseconds, 6.93 volts. 75 milliseconds, 7.2 volts. 80 milliseconds, 7.46 volts. See if I can get 85 in there. Move it down just a bit more. Still have a little bit of room. Wrong one. So a little bit of room on the oscilloscope here. At 85 milliseconds, I'm up at 7.71 volts. And 90, which is usually about the highest we can go for this, can barely squeeze that on. I'm at about 7.9 volts. So that completes the measurements, the data for T1. It's very different than T2. Notice that the amplitude of this pulse started high, went down to about 0, and it gets very large now, but the largeness increase definitely started to plateau off, and so that will be your core data for T1. The amplitude of the pulses, which were called out as a function of delay time between the A and B pulses. T1.